this video we are going to now look at wide sense non blocking switch. I will give you an example and of course, we will formally prove this time by using a state diagram. Basically, we will take the switch states and then based on how the transition happens from one state to another, you will be actually figuring out an algorithm by which a switch will never enter in a blocking state. Okay. So, important thing to know is that if it is a strictly non blocking switch, we have done this. Switch actually does not have a blocking state. You take any configuration, any input output connection map, any possible way the routes have been set up, switch is always in non blocking state. So, given a free input and free output port, you can always set up a connection. But there are scenarios where it is possible that you have a switch design where there are blocking states, but you can actually implement, you can operate the switch in such a fashion that switch will never enter into the blocking state. So, wherever whatever be those non blocked state, when a new connection comes in, you try to set up connection in such a fashion such that you will never enter into a blocking state. So, therefore, a switch technically operates in a non blocking fashion all the time just by using a suitable procedure, and this kind of switches are wide sense non blocking switches. Okay. So, important thing now the method which I will be using. So, we are now moving from here to wide sense non blocking. Here blocking states are not there. Here blocking states are present, but they are avoided. But they are avoided actually. Okay. Now, when I talk about this and I say I am going to prove it using a state diagram. Now, one of the problems with the states is, if for example, you take a simple 2 by 2 Bayes network. So, how many possible states a switch can be in actually? So, if you take a simple 2 by 2 crossbar, so what are the possible states? So, possible states are switch can be either in this configuration or in this configuration. Okay. There are only two possible configurations of a binary switch, is a binary switch. Okay. So, if I create a switch like this, now can you guess how many possible states this switch can be in? This is a Bayes network of a 4 by 4. This is a 2 by 2, there are two possible states 1 and 2. How many possible states are there in this case? Okay. So, each one of these 2 by 2 can be either in cross or in bar, and there are total how many switches? 1, 2, 3, 4, 5, 6. So, there are total 2 raised to power 6 possible configurations, okay, which implies 64 possible combinations which actually can exist. In this case, there are only two combinations which can exist. So, if you have any switch and of course, if you, this is not a 2 by 2, if it is k by k. So, total number of possible combinations with which connections can be mapped, if it is a strictly non blocking crossbar, it will be k factorial. So, the first output can be connected from the k inputs. Once this has been busy, they are only k minus 1 free. So, next one can be done with k minus 1 and so on. So, it will be k into k minus 1 into k minus 2 into 1 and so on. So, this will be k into k minus 1 into k minus 2 and so on till 1, so which is nothing but equal to k factorial. And if they are actually using such of them, say some number per stage, you can actually estimate some switches total number of stages. So, you will end up in k factorial raised to power total number of switching elements n which are used, these many number of possible configurations states are there. Okay. Even this actually has got 64. So, how we will do the analysis? There is such a large number of states. So, we use a concept called equivalent states. Now, if you carefully look, this 1 and 2 possible configurations, they both are technically same, they are not different. So, there is only one state actually. So, I can just simply twist input this one. So, I can twist here and this will end up in this particular thing. I can twist the whole switch, it still remains the same. I can twist this way, does not matter. I am not looking at a specific pattern, I am looking into the geometrical pattern which by translation or by moving the switches around or by rotating them can be converted from one form to another. They are all equivalent configurations. So, let me take an example of a 4 by 4 but 2 stage switch and try to give an example how the equivalence actually happens. What do I mean by rotation, translation or symmetrical transitions? In that, and the switch still remains in the same state, switch I am actually not at all changing any connections, okay. But still all of these states which will be coming will be all equivalent. So, let us take a 2 by 2 because once we know this particular notion of equivalence, I can use it to build up the non-equivalent states with one connection, two connection and so on. Of course, I have assumed that there is no connection. So, for a 2 by 2, let us start with this and then I will move to 4 by 4 with 2 stages. There are 2 inputs, 2 outputs. This is one state when no connection has been made. Second possible state can be when I make only one connection. Okay. Now, the connection can now be made in this fashion also. But if I twist it around, I will get the same thing back. So, these two are equivalent states actually. Okay. When I make two connections, I can make the connections in this fashion or I can make connections in this fashion. These two are also the equivalent states, I have to just twist it around and I will get this. So, there are only 3 states 1, 2 and 3 in this case. Okay. I am actually assuming here, I am also looking at if the connections are not being made, that is also one of the possibility. So, I am also counting this. Okay. So, there are total 3 states, non-equivalent states in this case which are present. When I actually gave you an example of that 2 raised power 6, I have not considered the states when the connections are not being made. Okay. So, we will also look into that. Now, let us do for 2 stages 4 by 4 system built using 2 by 2 crossbar and see how we can actually transform from one state to another state and both are equivalent, what the equivalence actually means. So, in this example I have taken remember this is a blocking system, this is not a strictly non-blocking, only 2 by 2 this element, this crossbar is a strictly non-blocking element, but this whole switch per se is a blocking system. So, a connection, for example, you can set up a connection. So, I am setting all 4 of them and trying to figure out the what do you mean by equivalence. So, I have set up a connection in this fashion. So, this is the connections the way it has been made. So, this is one state. Now, I can do the many things in this case. I can now swap between these two. I can take this particular 2 by 2 square switch and move it here, and this one I can move down. These two are remaining there. I am not changing any connection path. All wiring is maintained as it is. Switch topology will be equivalent. If you do this, so this switch has moved up, these two has been kept as it is. So, you can actually clearly see I have just simply moved it up. So, these two wiring remains the same. So, this one has to be brought to the bottom. So, this one will connect here, and this one will connect up and down. So, these two are equivalent, but what I have done is this transition. This is one possibility. Second possibility is I can do the flipping of the outputs. So, I have technically twisted the switch. So, once I do that, what I will get is this. So, since I have twisted this one, the outputs part, okay, let us actually flip the whole, twist the whole switch. So, inputs and output both are flipped. So, this will now get connected to the bottom, this was earlier connected to the top, and whatever was at the bottom one will come here. These inputs also will get changed actually. Okay. So, I will end up in getting this and this. And of course, this is going as it is. These two are also equivalent. I can simply twist the outputs also, that is possible, and keep the inputs as it is intact. So, if I do it here, so this is the switch being flipped, outputs being flipped. So, you will end up in getting a switch of, remember all these states are equivalent, all these are going to be equivalent. These are also equivalent. I can turn it around, I can turn it in this fashion, then also it will be equivalent. So, I can do it this way. So, I can just turn it around and then these two are also equivalent. So, that is what the equivalent states actually means. So, we will use this in our proof to formally reduce the number of possible states which can exist in the system. So, let us now move on to the example. This example actually has been taken from a paper which was published in Electronics Letters. So, you can search there actually and get this paper. So, on my notes which are available on the Brihaspati, the reference actually has been given for this particular one. This is a one page paper actually. So, the switch which is wide sense non blocking is this configuration. And this is not a 3 stage system, this is a 4 stage network. So, remember we had done closed network where there were 3 stages. So, here by just adding one more stage I am able to build up a wide sense non blocking switch. Okay. Actually it is a blocking switch, but blocking state is there, but we will avoid the blocking state. I hope you can actually see it and where the blocking is happening. Now, each one of these elements boxes is a 2 by 2 crossbar. Okay. So, when there is no connection, this is how it looks like. The way I will represent it, when there is no connection I will just simply draw the boxes, there is no line, so I need not show it, but topology actually is this. Okay. So, when the first connection is made from any input to any output, you can make the connection, you can make the connection this way, or if you want you can actually make the connection the other way around. With any other possibility you can make the connection in this fashion. Now, is this one connection thing equivalent? That is a question. So, I think I can transform any possibility, any one to one connection to only one single state. So, let us actually see if it happens. So, if I am going to make a connection like this, to which state I should be able to transform it to? So, maybe what I can do is I can do the swapping between these nodes and let us see what happens. If I do this, I will get so this actually has been swept down, this has been pushed down, these remains intact. So, these wiring will remain okay. So, let me not actually put these links okay fine, I think I should keep the links and use a different color for the one which the connection which has been made, so that you can trace it. So, this is the connection which I am talking about. So, I will actually draw the same diagram and let us see what happens. This is as it is intact, this is as it is intact, this is intact, this line will remain as it is, no change. Okay. Now, there is a swap which has happened. So, this line which was going up from this point should come to the bottom. So, this is come from here, this should come to the bottom of this line, and this switch has come down. So, this switch also has come down. So, this is connected from, and this is going out. Okay. So, this particular line actually will become the cross line from bottom to the top. Okay. This line will become the cross line. This particular line will become the parallel one. I think now the similar exercise has to be done here. These two have gone up. So, bottom one is the common thing. So, this one which has gone up will come to the bottom one. This one which is now down, the bottom up is taken care of. This one is now down from here, has to go to the top one. Okay, so I can transform it to this thing. I can now even rotate the switches, I told you, I can rotate the switches. So, I will rotate this one so that this twist can be taken care of. Okay. I will rotate this one, I will rotate this one, and I will rotate. In this case, I will rotate not the whole switch, I can rotate only the output part. In this case, I will rotate the output part to make it okay. So, this is the output ones which are being rotated, and here the switches are rotated. And for this one switch I am not still changing the wiring, the states are equivalent. So, I will end up in a configuration which will be, because I have twisted this. So, the bottom part must be connecting to the top part of this particular switch, the top part will become the bottom and connecting to this part. So, the top part is connecting as it is. So, both have been rotated, so this bottom part is connecting to the bottom part. Okay. In this case also it is not the switch, but the output which should be rotated actually. So, these two remains as it is. So, here the output has been rotated, so this will come here. We will actually connect it in this fashion. And I will rotate this one, this output will go as it is out. Okay. So, this bottom will connect with this and this will go with this, and this is a configuration. So, with one single connection, whatever way you want to set up, you can always transform it to this particular state. So, I define this as the base state for single connection. You can try out any other combination and this will turn out to be same. Let us do for another connection. So, let us do it here on this side. So, I have built up a switch . Okay. So, I am not actually going to draw the remaining thing, and maybe I should actually, so that you can understand what happens with the twisting and transformation. So, you can set up any other connection if you wish. So, I can set up something like this. Okay, let us see what all transformation will be required. So, normally you can need not do it in one step, I have done it in one single step. Okay. So, from here I have got something on this side, and then from there I have done, so I have done twisting actually of the switches here. For initially I did the translation or movement of the switches, so all of them come in the bottom. So, I can do both the things simultaneously also. So, we will do in the same fashion. First of all, we will do a translation of switches, Then we will look at the rotation of the outputs or the whole switch, outputs or inputs, so that I will ultimately end up in this particular configuration. So, I have to essentially swap this and this. Okay. Once you do that, you will end up in a configuration which is like this. So, you will have the top coming to this top one. So, this also has gone down. So, this bottom one will be coming switch, and then this goes to the top and goes out. Okay. And so, the remaining connection now has to be made. Okay, once I swap, sorry, this one has to be from the bottom side. Okay. So, its top part is connected to this one. This actually has gone up. So, the top part is connecting to the bottom one, the bottom part is connecting to the bottom part of this. So, it gets distorted in that sense, not that symmetric, and next step we will just do the rotations. So, this has been done. So, this top bottom part, the top part goes to the top, the bottom part has to go to the top of here. So, the bottom part here goes to the bottom, and okay, this one has gone down. So, bottom is taken care of, this one top part goes to the bottom part goes to the bottom here. So, you are able to transition from here to here. Now, you have to do all the rotations to straighten up the whole switch and come up with something as good as this. So, how this will be done? Okay. So, you will twist this one output side, you can twist this whole switch. Okay. This remains as it is, this remains as it is. I can twist this switch hole. Okay. I can twist this whole switch. I can twist the outputs here. Yeah, rest everything remains the same, and I should get up that particular thing, and you can see this is all common sense. Okay. So, once I do the twisting, I will get so the top connects to this one, the bottom connects to this one. So, this goes straight at the bottom. So, this one here, so I ended up in getting the same switch. So, you set up any single connection, you will end up in this state. So, we define this as a base state. Okay. So, we call it state 1. So, from state 1 Now I need not bother about when I do the second state, second switch here, second connection, what will be the new state, because all these single connection states are being merged into this. So I have to only bother about it and now set up the second connection, look at all possibilities and figure out the only equivalence between them. Okay. So I am now merging all the equivalent states into one single state, and thereby total number of states are being now restricted to very limited value, and therefore it becomes very easy to build up a state diagram, a state transition diagram. And once I can do that, I can identify which states are the blocking states and with what operation I will be able to block them, I will be able to avoid that blocking state. So let us do set up a second connection here and see what will happen. So what I will do is I will now create the whole diagram here, state transition diagram, but every time for figuring out the equivalent states I will be looking here. So once we have this connection, and you have I will be using few more colors for clarity. And I hope you should be able to see the blue color. So I will try drawing it, if it is not going to be visible I will erase and then do it with a different color. So let me see how we can set up the connection. So I can have the input coming from here, here or here. Okay. So what I will do is I have to do it very systematically. So I always try to actually set up the connection as far as possible from the bottommost input to bottommost input first, and then bottommost input to the topmost one, and so this side I am going from bottom to top and this side also from bottom to top and iterating with all possible combinations. Okay. And then trying to find out the equivalences with two connections. If I find out all possible non-equivalent states, so all equivalent states have been taken care of, and from there only I have to only look at the non-equivalent state. So I have got only one non-equivalent state here, all states with one single connection are being represented by this. Okay. So state transition diagram becomes far more easier. So let us do the connection. So from here if I want to set up a connection, how this will be going? This will go up naturally, and as I said that I would like to always go as far as possible. I can try going towards the bottom or I can start going towards the up. I will actually go towards up so that I can match with my notes and verify it. Okay. So if I go up, so I will be going up means going here, coming here, and then of course I want to connect to this switch. I can connect it in two different possible ways. I can actually always go up and therefore now I cannot go up and then connect to this switch, I have to go to bottom. So I can connect this one configuration. Okay. So this could be one possible non-equivalent states, but I have to look at other possibilities also. Let me iterate over those and see what will happen. So there is another possibility which I can draw here, and let us see whether these two are equivalent or not. So second possibility is it can go like this. Oh, I cannot actually have a connection to this one if I go downward, so it does not matter. Okay. It has to go to straight to the second one and then only this connection can be made. So I have actually exhausted all possibilities from this to this, there is no other possible way this connection can be set up. So, now let us keep this input and now iterate, let me go to the top. So, if I go to this or this does not matter, both are same. So, if I set up a connection from here to here and when I set up a connection from here to here, both are going to be the same states of the switch. Okay, so, only one of them need to be considered. So, let us see how this can be done. So, if I go up, then actually I can try going this way and set up a connection. So, perfect, this is another possible state. So, I am actually going to find out every time new non-equivalent state I will put it. So, the first one is this. So far I have not got, I cannot actually transform by any way by rotating the switch or moving here and there, whatever I did, those transformation cannot come from here to here actually. Okay. So, this is the second possibility. What could be the other one? Let us see. So, we can have so next possibility is goes up, it goes down, it goes up. Oh, this is the way also I can make the connection from here to here. Now, can I actually by doing translations or anything can I move it here? Possibly I cannot, there is only one common switch through which the two connections are moving here. Here they are two in different sets, here it is in first and third stage. So, this certainly cannot be equivalent actually. Okay. This certainly cannot be equivalent. So, this is a different configuration than this one. So, what are the other possibilities? Let us see. So, I actually draw a first connection. So, now I have already exhausted from this input to all possible output, these two does not matter output, so far it reaches here it is okay. Okay. So, now I have to look from the top, this one. So, let us see what are the combinations which I can get. I can try going actually first of all from the top side, I can connect to this switch first. So, how I can do it? I can go straight and connect. Oh, but you can clearly observe if I actually twist it around, make these as inputs and these are outputs, I will end up in this particular configuration. Okay. So, these two are the equivalent states. So, I can actually now bound it, this is the equivalent state to this one. Let us look at other possibilities. So, I wanted to connect to this, but I actually went straight first and then tried. Can I now go straight first and then can I go down and make a connection? I cannot possibly. If I come here, I have to go here. So, I cannot do it this way. So, now I am exhausting all possibilities. Now, this is a one possible option, but amazingly if you rotate this, you will end up in this particular configuration. So, this is also an equivalent state to that. So far we have found only 3 non-equivalent states. Now, let us connect from here to here and see how many non-equivalent states are possible. Okay. So, if we do it now, connecting it in this fashion. So, I have actually made the connections, remember, here from the top one to bottom one, and I found in both possible ways I am actually coming back to already discovered states. So, now go from top to top, let us see what all states I can make. So, I can actually go straight, that is a one state thing. There is no way probably I can actually come to this or this state, okay. Both inputs and both outputs are from different switches in the input and output stages, okay. So, this certainly is another possibility. Then can I try some different route going from bottom and doing it? So, remember, I am actually exhausting all possibilities, and wherever it is turning out to be an equivalent thing, I am just not considering if the equivalent already has been discovered. So, I can try now going this way to bottom, no, it is not possible to set up. So, I can try this way. Now, amazingly, these three states which I have discovered earlier, they actually had two inputs going from the same switch in the input stage. Now, this is not happening in this case, so this certainly cannot be equivalent to those. There is no way I can, by any transformation I can move from here to there, and this also certainly is not equivalent to this. So, let us look at other possibilities. Still I have not exhausted everything, I have to now look, if I go to bottom, what will happen? So, searching, this time I actually go from here to bottom. So, I cannot go parallel, I have to go here, only way I can go it in this fashion, but you turn it around, you end up in this state, okay. So, you will have, I have now exhausted all possibilities for the second connection. So, only valid, only what we call non-equivalent states are with one connection is this one. With two connections I have now 5 possibilities, 1, 2, 3, 4 and 5. All other states with two connections can be assumed to be represented by any one of these 5.